In this video, we're going to discuss the product and quotient rules for use with polynomials. Now, the product and quotient rules can be used with all types of functions, but today's lesson is going to focus specifically on its use with polynomials. Now, if we consider the function y equals x times the sum of x plus 1, you'll notice that this is a product of two separate functions. We do know the derivatives of each of those functions. The derivative of x is just 1. And the derivative of x plus 1 is just 1. However, if we try to assume that the derivative of the entire quadratic equation is just the product of those derivatives, we would be incorrect. For us to have a derivative of just 1, we would have to have a function that is linear, such as x plus 7. X plus 7 would have a derivative of just 1 plus 0, so 1. So we know that a quadratic equation should not have a derivative of just 1. If we were to then distribute the x across the x plus 1 sum, we would see that using the power rule that we learned earlier, the derivative of x squared would give us the 2x, and the derivative of x would give us the plus 1. So we have choices. We can either always distribute, always simplify the equation, or we need to learn a rule for the product. Now, some people think, well, I'll just always distribute them out. That would be okay if we weren't trying to find the derivative of things like x plus 10, say, to the 100th power. It's not always possible to multiply everything out without learning a new rule. So we're going to learn 3 different rules this week. The power rule we learned, the product rule and quotient rule, and the next week we're going to learn a 4th one, the chain rule. So in example 1, we have choices. We can either distribute the entire thing, so we would have x cubed minus 2x squared plus 3x by distributing the x, and then a minus x squared plus 2x and minus 3 by distributing the negative 1. So, simplified out, we get y is equal to x cubed minus 3x squared plus 5x minus 3. Then we could take the derivative to get 3x squared minus 6x plus 5. However, there is another option. I like to jokingly call this the wife swap rule. A product starts with a p, so we're going to end up with a plus. But basically, whenever we have the product of two functions, I'm going to take the derivative of the first function and align it with the second function, the derivative of the second function and align it with the first function. So my joke is that each one swaps to get the other one's derivative. So for our purposes, in our original, we have x minus 1 as one of our functions, and the derivative of that would be 1. We also have x squared minus 2x plus 3 as one of our parts, and the derivative of that would be 2x minus 2. So in my swapping process, I'm going to put the first function with the second function's derivative, and the second function with the first function's derivative. So we're going to kind of cross them over. So that makes my derivative x minus 1 times the quantity 2x minus 2 plus x squared minus 2x plus 3 times the quantity 1. So my simplified derivative would be 2x squared minus 2x minus 2x plus 2, and then multiplying 1 would just give us the second term, x squared minus 2x plus 3. So altogether, notice that we got the same derivative. Altogether, we have 3x squared We have minus 2 minus another 2, so minus 6x. And the plus 2 and plus 3 makes plus 5. Now you're probably asking yourself, why would I even want to learn that? But remember, not everything that we have is going to be as easy to distribute or simplify as these two terms of the polynomial. And some things cannot be distributed at all. So later we'll learn derivatives that involve sine and cosine, in which case there would be no way to distribute an x squared multiplied by a sine of x function. So this is a crucial concept to understand. Okay, so for this, for example 2, I know that the square really means that I'm multiplying the term times itself. So the first one has a derivative of 2x minus 1. The second one has a derivative of 2x minus 1 also. Remember that technically I'm still swapping them up. So we're crossing them over to get each other's derivative. So I have y prime equals the first term times the second derivative plus the second term multiplied by the first term's derivative. What's nice about this method is I really don't have to distribute that at all. Both of these terms are identical. That means I really have 2 of the 2x minus 1 times x squared minus x plus 1. We actually prefer factored form as long as it's simplified factored. Up above, we didn't have a simplified factored form because none of those terms were the same, so we had to simplify it out. But for this particular one, we actually prefer that we leave the factored form since they are all perfectly prime factors. Okay, so for example 3, the derivative would be 4 minus 4x. The derivative of the second term is just going to be 3. So for now, since we're just working on our product rule, I'm not going to go through and simplify everything, because that's really more of an algebra skill that you should have come in with to the course with a prerequisite. So hopefully your algebra skills have been practiced for the last 3 years. So our derivative is the first term times the second term's derivative plus the second term multiplied by the derivative of the first term. And then algorithm from there would simplify this out. Okay, so for example 4, the derivative of the first term is 7/5 x. When I subtract 1, I'm really subtracting 5/5, so that leaves me with 2/5. And the derivative of the second term is 10x minus 1. So again, using my wife swap here, the first term with the derivative of the second term, the second term with the derivative of the first term. So our derivative in the unsimplified form is the first term times the derivative of the second term plus the second term times the derivative of the first term. Now, something I really want to point out to you here. On the AP exam, when you're doing the product and quotient rules, especially, they're looking for you to do this process of the first term times the second term's derivative, the second term, and the first term's derivative. If you were to have written this with a dot for multiplication, your answer is incorrect because PEMDAS tells us that that means these two terms are multiplied but not the minus 1, and these last two terms will be multiplied, not the 5x squared. Do not use a dot for multiplication in this course. Make sure that you're always using parentheses for multiplication. Otherwise, your answer is incorrect, and you're going to lose 2 out of 3 points on this problem. They're going to give you a point for recognizing that you kind of did the product rule, even though incorrectly. But they're not going to give you the second point for the product rule, and they're certainly not going to give you a final point for an incorrect answer. Okay, so for example number 5, the derivative of the first term, the 3 multiplies by the 2, we end up with 6x minus 2. The derivative of the second term is negative 20x cubed plus 6x squared minus 14x plus 1. Definitely not something I would want to try to multiply out and simplify and risk getting the answer wrong because of my algebra. So my derivative will be the first term times the derivative of the second term. Plus the second term times the derivative of the first term. Now, another benefit to knowing this method and trying to avoid as much algebra is that if, for example, I had asked you for the derivative at 1, I wouldn't have to simplify the algebra. I would just have to do the arithmetic. So at 1, I would have 3 minus 2 plus 5, 6. Negative 20 plus 6, negative 14 plus 1, negative 27. Plus negative 5 plus 2, negative 7 plus 1 plus 2. So negative 7. 6 minus 2 be 4. So this I could simplify relatively easily and really never have to simplify the algebra, just simplifying arithmetic. Okay, so now we're going to talk about the quotient of two functions. So similar to the product rule, if we start assuming we could just take the derivative of each part separately, for example, and get 2x over 1, 2x we know is the derivative of x squared. So it can't possibly be the derivative of this rational function. If I were to graph on my calculator the original function and the derivative of the original function, just to see what they look like, you'll notice that this is my y function. This is the derivative of that function. It absolutely does not equal x squared. X squared would be a parabola. It also does not equal the derivative of x squared, which is 2x. 2x would be a straight line. This derivative is definitely not a straight line. So we need to use a different rule. This rule looks very similar to the wife swap rule we just used, but remember the product was plus, The quotient is a minus sign. The way that I tell my students each year to memorize this is you're going to memorize this as a rhyme, so a mnemonic device. It's the low, or the denominator, times the derivative of the high, the numerator, minus the high, the numerator, times the derivative of the low, and that's all divided by the low squared. Okay, so you're taking two derivatives, just like you did before. One derivative of the first, one derivative of the second, and that's your numerator. Your denominator is not a derivative. So again, that's the low times the derivative of the high minus the high times the derivative of the low over low squared. So low d high minus high d low over the square of what's below. So only the d's are derivatives. Low d high minus high d low. Okay, so we're going to do a few of these and check with the power rule. So my high is 3. The low is x squared. The derivative of the high is 0. The derivative of the low is 2x. So using our rhyme, we have low d high minus high d low over the square of what was below. So low squared. Now, since anything multiplied by 0 is 0, our first term goes away. We have negative 6x on top, x to the 4th on bottom. That simplifies to negative 6 over x cubed. Now, we could have done this one by rewriting it as the power rule. And sometimes that's better than using the quotient rule. My derivative then would be negative 6x to the negative 3, which is equivalent to the answer we got using the quotient rule. So if you can simplify out the rational function, it's always going to be easier to do that than the quotient rule. Here, my high is 2x to the 4th minus 1. So the derivative of high is 8x cubed. My low is x squared, so the derivative of low is 2x. So my y prime, using our rhyme, is low d high minus high d low over the square of what was below. That makes this 8x to the 5th minus, and I have to distribute that 2x, and I have to make sure I distribute the negative. So minus 4x to the 5th, and minus a negative 1 makes a plus 2x over x to the 4th. So that simplifies out as 4x to the 5th plus 2x over x to the 4th. Because I can factor out an x, I can cancel, and I get 4x to the fourth plus 2 all over x cubed. Now this problem might have been easier to do without the quotient rule because I could have divided this in and had 2x squared minus x to the negative 2. That derivative would have been 4x plus 2x to the negative 3, but it wouldn't have had a common denominator. And you tend to see these written with a common denominator because of our horizontal and vertical idea. We very often want to know where we have horizontal and where we have vertical tangents. Horizontal is if the numerator equals 0, and vertical is if the bottom equals 0. So we tend to want to have them with a common denominator, which means that the quotient rule is very handy for that. Now, for example 3, I can't simplify this. There is no way to split the denominator up. I can split the numerator with the way that we did with number 2, but not the denominator. So for this one, my high is 1, so the derivative of high is going to be 0. My low is 2x cubed minus x, so the derivative of low is 6x squared minus 1. So my slope, dy dx, is low, d high. Notice again my use of parentheses, never a dot, minus high, d low, over the square of what was below. So we're kind of going to do a wife swap, but the order matters this time. Because we have a minus sign, it is extremely important that you get these in the right order. So it's important that you memorize that mnemonic device, the low d high minus high d low, and what it means. So my first term is a 0. My second term, the negative distributes. I can leave the bottom in the unsquared form because we prefer the factored form for finding zeros. A 0 over the denominator would be an undefined slope. For example 4, I have my high and the derivative of high. I have my low and the derivative of low. So using my mnemonic device, dy dx equals low d high minus high d low over the square of what was below. Simplifying that out would be 5x squared minus 5. I have to remember to distribute the negative 1 and distribute the 2x. Let's pick a different color for that. That red and pink did not show up very well together. So I have to distribute both of those across the 5x plus 2. Okay, so we have 5x squared minus 5 from the first term, negative 10x squared, negative 4x, all over x squared minus 1 quantity squared. So we end up with negative 5x squared, negative 4x, negative 5, all over x squared minus 1 quantity squared. Now for example 5, I wouldn't use the quotient rule. The reason I wouldn't use the quotient rule is because I can relatively easily turn this into the power rule. Because x squared is being divided by root x, and the plus 1 is also being divided by root x. So since root x is a half power, that means this is x to the 1.5, or 3/2 power. Since this is just on the bottom, simply means we have x to the negative half. So for this one, I would use the power rule. Subtracting 1, I'm left with a half. Bringing the negative half down to the front. Subtracting, I get negative 3/2. And if it were a free response question, I could leave it that way. Otherwise, I have 3 square root of x over 2 minus 1 over 2. Remember, roots are on the bottom, so it's a square root, x cubed. And if I absolutely had to find a common denominator, I would need to multiply by the square root of x cubed. So the square root of x to the 4th would leave me with 3x squared. So then my numerator would be 3x squared minus 1, and the denominator would be a combined 2 square root of x cubed. But most of the time, you're going to be able to leave that answer just like this. Okay, so we're going to go through a few of these for practice. But for the most part, you're going to work these on your own to double check and be sure with the answer key that you're understanding. So for number 1, actually we'll look at number 2, it's a little trickier. For number 2, this is not something I would really want to do the quotient rule for. Tricky part about this isn't the rewriting, it's the fact that pi looks like a symbol, like a variable, and it isn't. Remember, pi is a constant. We even know a value for pi, an approximate value. So treat pi just like you would the number 3. If I bring this down and multiply, I get negative 3 pi x to the negative 4. For this second part, I do not get 2 pi. Pi squared is a number, and the derivative of any number is 0. That means that my derivative for this part is just negative 3 pi over x to the 4th. So you want to watch for that one. So number 3 would be something that I could do with just the power rule. I really wouldn't need the quotient rule. Number 4, if I did the derivative of the first, I would get 2. The second would give me 3. That means my y prime is the product rule, or our wife swap. So the first term times the derivative of the second term, the second term times the derivative of the first term. Make sure you're always using parentheses for multiplication and that you're remembering to distribute. So my derivative is 12x plus 5. And I didn't have to do any crazy FOILing at all. Let's look at number 7. Okay, number 7 is an example of something that could not be simplified, whereas number 9, you really could simplify and use the power rule. So for 7, the derivative of the top is 5. The derivative of the bottom is 2x plus 4. So my derivative is low d high minus high d low over the square of what was below. Okay, now remember, you're never going to simplify this part, ever. Leave it. The top, you would need to do the algebra to simplify, but we won't spend time on the algebra today. Number 10 cannot be simplified. So you can't do it with simplification. Can't be any simpler. You're going to have to use the quotient rule for that one. And you can check your answer with the key. Okay, so let's practice making the equation of a tangent line at the indicated point. And you can use your calculator to confirm the results. So we'll look at that together too. So the derivative of the first part, 2x minus 4. The derivative of the second term is 4. So y prime is the first term times the derivative of the second term plus the second term times the derivative of the first term. Now, since you're being asked to use x equals 1, you don't have to simplify the algebra on this. You're going to go directly in and substitute x as 1. That gives us 1 minus 4 plus 2, quantity times 4, plus 4 minus 1, quantity, times the quantity 2 minus 4. That makes all of our simplification just arithmetic. So we have negative 1 times 4, 3 times negative 2. So negative 4 plus negative 6 is negative 10. So using point-slope form, y minus negative 3 makes plus 3 equals negative 10 x minus 1. Now, on your calculator, what's really nice about the calculator is if you were to put a function in, and you could type it in exactly as it reads on your paper. Whoops, fix that. So x squared minus 4x plus 2, 4x minus 1. So notice I've typed exactly what was on my paper. I then need to graph, and I should see a cubic function because our powers overall were cubic, and 1, negative 3. I'm then going to choose to draw. Two things I can check though. I can trace and calculate, so second, trace, and notice the sixth option down is dy dx, but it's finding it at 0. That is the default for every new graph. We want to find that slope at 1. So if I type 1 in, there's a little bit of rounding error on my calculator because calculators that are the TI-84 don't have a computer algebra system. They're doing an approximation of the derivative, but we can tell that negative 10 was a good answer. What I can also do is do second again, and instead of calculating, I'm going to choose to draw, and I'm going to ask the calculator to draw the tangent line, which is number 5. I again have to tell it where. It's waiting for me. So I'm going to tell at x equals 1 and press enter. and it's going to draw the tangent line for me. The other thing that it does, which is nice, I'm going to close the calculator down, is it actually tells me the equation of the tangent line. Now, I want my answer to be left in point-slope form. However, I can still use some algebra to check my answer against the calculator. I have to remember to distribute the negative 10. And then if I subtract 3 from both sides, negative 10x plus, plus 7. My lines are kind of running together a little. Let me see if I can straighten that up a little bit. So y equals negative 10x plus 7. So even though my calculator is not as smart as we would like to hope, I can tell that that should be negative 10x, and this should be plus 7. There is a video online inside of our course Module 2 that reminds you how to use your calculator to find slope. It's a good way to check, even though you're not going to be allowed to use your calculator. For 2/3 of your tests and quizzes, it's always good to be able to do that as a check. Okay, so for this one, we're going to do 2 out of 3. Determine the points at which the graph has a horizontal tangent. So a horizontal tangent, remember we're going to use our Hoy of x. So a horizontal tangent is a 0 slope and would be a y equals equation. So for number 13, my slope, when I bring the 3 down, it's going to cancel. We have 8x squared plus 10x minus 3. The horizontal slope is when that derivative equals 0. That means we need to be able to factor this out. Okay, so in order to factor this, we need 8x squared plus 10x minus 3 equal to 0. We can either factor by grouping, or if you're more comfortable with a leading coefficient, if not, then you can do 8 times negative 3 would be negative 24. So you're looking for factors that would make 10. So we need one positive and one negative so that we end up with a negative number. So you have 1 and 24, 2 and 12, 3 and 8, 4 and 6. Now, to beat the confusion here, if I choose 4 and 6, to get 10, I need them to have the same sign, and we said we need opposite signs. So we're going to have to choose 2 and 12. So I know that my factors of 3 can only be 3 and 1. When I'm looking for my center part, it's the outer and the inner that I'm looking at. So to get 12, I'm going to choose 4x. And to get 2, I'm going to choose 2x. So 12 and 2. I need a positive for the 12 and a negative for the 2. So x would equal 1/4, or x would equal negative 3 over 2. So to find the point, I would have to take this and substitute it back in and get f of 1/4, f of negative 3/2. Since we're really working on the calculus now and not the algebra, I'm not going to go through and find those values for you. You can check them online, however. So for another example, let's look at 14. I'll pick a new color so it doesn't run together. The derivative of our high part is 2x. Derivative of the low part happens to also be 2x. My slope is low d high minus high d low over the square of what was below. So now, the nice part is if we're looking for a horizontal tangent, we only care about the numerator. Because remember, 0 over a number is what gives us a 0 slope. If we do 0 on the bottom, we're going to get undefined, and that would be vertical, which is not what we're looking for right now. That means that I can really focus only on the numerator. So if I distribute 2x cubed plus 2x, I distribute a negative and the 2x. I get negative 2x cubed and positive 6x. It's very nice. Some of it cancels. I get the numerator to be 8x and the denominator, remember, we never simplify out. So for the horizontal, I only want the numerator equal to 0, so I only get x equals 0. So for our point 0, we can go back to the original. If we put 0 in for x, we get negative 3. So we have found the point where we have 0 slope. That means we also have the equation of the horizontal tangent. Remember, we said a horizontal is only a y equals line. So that means that y equal to negative 3 is the exact horizontal tangent. Try not to confuse horizontal tangent and vertical tangent with horizontal and vertical asymptotes. A tangent line needs to actually have a point. Okay, one of College Board's favorite things to do is to ask you to do the rules and to understand the rules without a specific function. So you can't just memorize the power rule and that be okay. So remember, addition and subtraction are just normal, but products and quotients, we have to have a rule. So you're going to think of your product rule, P for plus, is just our wife swap, and your quotient rule is our mnemonic Lodi high. So f prime of x, in this case, is 4, because it's just a constant. Remember, we can hold a constant. We don't have to do the product rule unless it's two functions. So this isn't really two functions, it's just 4 times. And the derivative of g is g prime, minus a half. The derivative of h is h prime, and the derivative of 1 is 0. We're looking for f prime of 3 for all of them. So our notation can't mix up the 3's and the x's. So we have to be very careful about that. When we're taking the derivative in terms of x, all of our terms are x terms. Then we can substitute in the 3, and then we can go and get values from the table for g prime of 3, which is negative 2, and h prime of 3, which is pi. So we have negative 8 minus pi over 2 is f prime of 3 for this problem. So you're going to use a similar process for your products and your quotients. So we'll do one more quotient together. So now on this one, if I were to skip ahead and do f prime of 3, that's okay, but then my notation has to be in terms of 3 the entire time. So f prime of 3 equals low, which can't be x now, has to be g, d high. Now I have to have parentheses for that. The d high is g prime of 3 minus h prime of 3. Minus the high, which has to stay in parentheses, times the derivative of the low. And that's all over the square of what was below. So for h prime of 3, we have the low, the derivative of the high, minus the high, times the derivative of the low, over the square of what was below. So simplified out, we're going to have negative 8, negative 4 pi. A negative times a negative makes a positive, so positive 2 times 1 over 16. So we have negative 6, negative 4 pi over 16. If I factor out a 2, I can factor and cancel a 2. I would have negative 3, negative 2 pi, all over 8. Okay, for this last one, notice we have a quotient that can't be simplified. So my high is u times v. That means the derivative of the high is a product rule. It's the first swapping with the second. So it's the first with the second one's derivative and the second with the first one's derivative. So they wife swapped up there. Now, the low is w, and the derivative of the low is w prime. So now, after all that crazy hard work, we have to do our mnemonic device. It's low times the derivative of the high minus the high times the derivative of the low over the square of what was below, not a derivative. So we can eliminate right away answer choice A for not having the correct denominator. Now most of these have the alphabet in order, but we're going to have to distribute first. So we have W, U, V prime plus W, U prime V minus W prime U V all over W squared. And then we can worry about alphabetical order. Now we can't change the order of our terms around necessarily, but we have a U with a V prime and a W plus a U prime with a V with a W minus a U, V, W prime all over W squared. So let's look for our individual terms. I need to have a U, V prime, W. I have that here. I have that here. I have it here because I need a positive U, V prime, W. So that's wrong. So we can eliminate this one. I definitely need 3 terms on the top, so I can eliminate this one. I also have on the top, besides the U, V prime, W, I have a U prime, VW. So U prime VW is positive. But now my last term needs to be a negative, UVW prime. So this one's wrong. We can eliminate it. Our choice is E. That's it for today's practice on product and quotient rule with polynomials and generic functions.